In Unit 1, I plotted chlorophyll A concentrations in the Chesapeake Bay dataset, and they seem to follow a Gaussian or normal distribution, popularly called the bell curve. I said we could use our skills as data detectives to model this. I'll discuss this in more detail in this three-part series I'm calling All About the Bays. This first part focuses on probability distributions. We'll begin our story with Adolphe Quetelet, a Frenchman who saw the bell curve everywhere and who believed he could explain a lot about disease, education, even crime rates by using the normal distribution. In 1835, Quetelet published a book from which this illustration is taken. He proposed that many human qualities follow the bell curve and referred to the idealized person at its center as the average man, about whom he wrote, "The average man serves as a type to our kind. Every individual has his particular constitution, which depends also on his organization and his mode of existence. It is interesting to know each of the elements which concern us individually, and we have a general interest in knowing each of the elements which bear on the average man." There's quite a bit to unpack in this statement. Not only was Quetelet suggesting that we could use the average man to understand individual differences, but also that the bell curve is not constant. It shifts depending on the context of time, place, and community. Quetelet's book caused a stir around Europe and influenced another data detective across the channel in England named Francis Galton. Galton used Quetelet's ideas to analyze the theories of evolution and heredity raised by Charles Darwin. Darwin was a distant cousin of Galton's. Each traced his lineage to Erasmus Darwin, who was twice married. One can only imagine the conversations around the table during their family reunions. Galton in 1877 delivered a lecture in which he said, "It was to Quetelet that we were first indebted for a knowledge of the fact that the amount and frequency of deviation from the average tends to conform to the mathematical law of deviation." To communicate Quetelet's work without overwhelming his audience, Galton invented the best tool for science communication I know of, a device I am calling the Galton box. From the top funnel of the device, Galton dropped a series of balls. Each ball would encounter rows of pegs on its downward journey and would bounce left or right randomly at each peg. This is a picture of the original Galton box at the University College in London. Let's see the device in action. As you can see, a bell curve has formed at the bottom of the box. Why? Because of two factors, one creating order and another generating randomness. Order comes from gravity, which causes the ball to go straight down. Randomness is generated from the series of 50-50 chances a ball goes left or right as it encounters a peg. Very rarely does a ball consistently and randomly keep heading to the right or to the left. Most randomly head right, then left, and right again, so the majority end up smack in the middle of the bell curve. I've spared no expense for this course, and I built a Galton box entirely out of R. My R commands are relatively simple. To provide order, I directed each ball to go from point to point down the y-axis. To provide randomness, at each row, I drew one ball from a probability distribution called the binomial, the computational equivalent of tossing a fair coin to determine whether a ball goes right or left. The main point is that through computational modeling, we are able to simulate a physical event in the real world. This is our job as data detectives, whether that reality is the Galton box or the distribution of chlorophyll A concentrations around the Chesapeake Bay. How do we do this? To begin answering this question, let's look more closely at the randomness in my Galton box. To keep the animation short, I programmed for relatively few balls in my Galton box. I could have approximated a better binomial distribution with a 50-50 chance by using 1,000 balls, as shown in this histogram. If you've forgotten what a histogram is, refer back to the video for Unit 1. So we share the same vocabulary. Let's call this 50% probability the parameter for this distribution. I could generate a random outcome with more heads by assigning this parameter a value of 70%. A parameter value of 20% would generate fewer heads. We use this binomial distribution to simulate binary outcomes such as heads or tails from a coin toss, or whether one loses weight by following a vegetarian diet in a field trial. But what if we wanted to track the amount of weight one gains or loses? This could take any value such as -5 for losing 5 pounds or +10 for gaining 10 pounds. To model this, we would use a normal distribution, the shape of which depends on two parameters, the mean or average weight loss in our field trial, and the variability around this mean. And if we wanted to count the number of people who lost weight, we'd use the Poisson distribution, which only allows for positive numbers and the shape of which depends on a single parameter. The two main points in all this is that choosing the appropriate type of probability distribution depends on the problem we are investigating, complemented by our evaluation of the data. Secondly, the parameters determine the shape of the distribution. In Unit 1, we also looked at the mathematical relationship between the nitrogen ratio, our predictor, and the response variable chlorophyll A. We approximated this relationship with a line defined by a slope and intercept. The slope indicates how the predictor and response vary together. The intercept is the response variable's value without the predictor's influence. We knew this was a rough approximation. Most actual measurements of response variables deviate from the modeled value. If for each modeled value we took the residual, that is, the actual versus the modeled value, these residuals would follow a distribution. To summarize, similar to my computational Galton box, our model contains a component imposing order as approximated by a linear relationship showing how the predictor and response variables are related. Our model also includes an approximation of randomness, estimated by the probability distribution of residuals, centered around each predicted value on the line and defined by one or more parameters. As data detectives, our mission, should we decide to accept it, and we should, because by learning these tools, an exciting world opens up for us, is to identify the form of this linear relationship, along with its intercepts and slopes, and the form of this probability distribution, along with its parameter values. Let's move on to part 2 of this series and learn about this sorcery called Bayesian analysis.